Hello, and welcome. Tonight, we're going to explore some truly fascinating things about moons, those silent partners that orbit planets all across the cosmos. These incredible celestial bodies, from the ones we see every night to others far away, influence their worlds in profound ways, shaping atmospheres, creating tides, and even hiding entire oceans below their surfaces. Some appear ancient and scarred, quietly observing billions of years of cosmic events. Others show signs of constant change, with active volcanoes, powerful geysers, or vast, shifting ice sheets. Our own moon is just the start of this story. As we venture further out, we discover places like Titan, with its mysterious liquid methane seas. We'll learn about Europa, which might hold a secret ocean, and Enceladus, constantly launching bright plumes into space. Moons come in all sorts of forms, some resemble potatoes, others look like sponges, and a few even glow with their own auroras. It's possible that some of them might even contain the necessary chemistry for life to begin. Understanding moons helps us uncover the hidden narratives of the entire solar system. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our planet's moon, the one that lights up our night sky, is actually moving away from us. It's a very slow process, almost imperceptible on a human timescale, but it's happening all the same. Each year, our lunar companion expands its orbit, pulling away from Earth by about 3.8 centimeters. That's roughly 1.5 inches every 12 months. This separation happens because of a complex interaction involving our planet's spin and the vast bodies of water on its surface. As Earth rotates, its oceans are pulled by the moon's gravity, creating the familiar bulges we call tides. These tidal bulges don't stay perfectly aligned with the moon, though. Because Earth is spinning, our planet's rotation carries the tidal bulge a little bit ahead of the moon's direct gravitational pull. This slight offset means that the gravitational attraction between the Earth and moon isn't perfectly balanced. The leading tidal bulge, positioned slightly ahead of the moon, effectively tugs on the moon, giving it a tiny push forward in its orbit. This constant, gentle nudge adds a bit of energy to the moon, causing it to move into a slightly higher, wider orbit. It's a bit like pushing a child on a swing. Each push adds a little energy, making the swing go a bit higher. Over immense periods, this effect has significant consequences. If we could rewind time, billions of years ago, our moon would have been much closer to Earth. Imagine looking up at the night sky then. The moon wouldn't just be a bright disk. It would appear much larger, perhaps even filling a noticeable portion of the sky. Its presence would have been far more dominant, casting brighter light and exerting a much stronger gravitational influence on our oceans. The tides back then would have been dramatically higher, surging and receding with incredible power. This closer proximity also meant that Earth was spinning much faster. Days were significantly shorter, perhaps only a few hours long. The moon's current retreat is also slowly but surely extending our days. As the moon gains orbital energy and moves away, Earth loses a tiny amount of rotational energy. This means our planet's spin gradually slows down, making each day a little bit longer. The change is so minuscule, about 1.7 milliseconds per century, that you'd never notice it in your lifetime. But over eons, it adds up. In the unimaginably distant future, Earth's days will be considerably longer than they are now. This ongoing celestial dance serves as a powerful reminder that nothing in the cosmos is truly static. Even something as seemingly constant as the moon's path around Earth is perpetually shifting, quietly transforming the skies our ancestors saw and the ones our future descendants will inherit. It's a slow, cosmic evolution unfolding before our very eyes, if only we had the patience to observe it across geological time. Our moon, the familiar orb in the night sky, wasn't always the desolate, airless body we observe today. Billions of years ago, in its much younger days, it possessed a different character. Scientists have gathered evidence suggesting that the moon once had its own atmosphere, a thin but definite veil of gas enveloping its surface. This ancient lunar atmosphere was born from intense volcanic activity. During that tumultuous period, numerous volcanoes erupted across the moon's surface, spewing vast quantities of gas and molten material into space. These powerful outgassings released elements like carbon monoxide, sulfur dioxide, and water vapor. Over time, enough of these gases accumulated to form a transient atmosphere around the moon. While this atmosphere wasn't as thick or as dense as Earth's, it was substantial enough to persist for millions of years, an astonishing thought for a body now known for its vacuum-like environment. However, this early lunar atmosphere was ultimately too fragile to last indefinitely. The moon's relatively small mass meant its gravity wasn't strong enough to hold onto these gases for eternity. Gradually, the atmospheric particles, buffeted by solar winds and lacking a strong magnetic field for protection, began to escape into the vastness of space. Bit by bit, the gases dissipated, leaving the moon as the exposed, airless world we recognize. The process of atmospheric loss was slow, but relentless. This temporary atmosphere, despite its short lifespan in cosmic terms, might have played a crucial role in shaping the moon's present-day features. Researchers hypothesize that during this period, water molecules, released by volcanic activity or delivered by cometary impacts, could have been trapped and transported by the atmospheric currents. These molecules might have then settled into permanently shadowed craters near the lunar poles. These deep, sunless regions act as cold traps, where temperatures remain so frigid that water ice can survive for billions of years without sublimating back into gas. So, when we gaze at the moon today, perceiving it as a timeless, unchanging entity, its ancient history reveals a more dynamic past. It was a world that briefly breathed, shrouded in a gaseous envelope, before eventually succumbing to the harsh realities of space and falling silent once more. It's a testament to the moon's complex geological evolution, a story written in its rocks and potential ice reserves, hidden from casual view. Not every moon in our solar system is a perfect sphere, gracefully rounded by its own gravitational pull. In fact, many smaller satellites possess incredibly strange and irregular shapes, often resembling cosmic potatoes or even futuristic flying saucers. Take Phobos, one of Mars's two tiny moons. It's a lumpy, uneven rock, far from spherical, looking for all the world like a misshapen tuber floating through space. Then there's Pan, a diminutive moon orbiting Saturn, which boasts an appearance uncannily similar to a ravioli or a tiny flying saucer. It even has a prominent ridge running around its equator, making it look almost artificial. This peculiar bulge is thought to be formed by material it sweeps up from Saturn's vast ring system as it carves its path. These bizarre and often playful forms arise because smaller celestial bodies lack sufficient gravity to sculpt themselves into a perfectly spherical shape. For a moon to become round, its gravitational pull must be strong enough to overcome the structural strength of its material, essentially crushing any irregularities into a smooth orb. Without that powerful internal gravity, these smaller moons retain their original, chaotic configurations. They can be jagged, bumpy, elongated, or even disc-like, reflecting their tumultuous origins. Many of them are thought to be fragments from earlier, more violent collisions, essentially cosmic debris that eventually coalesced or was captured by a larger planet. Others might have been wandering asteroids, pulled in by a giant world's immense gravitational grasp. Their unique silhouettes are not just curiosities, they are direct physical records of their formation, frozen in time. While the giant moons, like Jupiter's Ganymede or Saturn's Titan, feel like entire worlds in their own right, these smaller, irregularly shaped companions feel more like leftover pieces, fragments from the grand cosmic construction project that built our planets and solar system. They remind us that the universe is full of diversity, even in the smallest of its orbiting bodies. Each one, with its quirky form, tells a part of the grand story of creation and chaos in space. Beneath the intricate, fractured icy crust of Europa, one of Jupiter's most intriguing moons, lies an astonishing secret: a colossal global ocean. The scientific community has gathered compelling evidence pointing to the existence of this vast subsurface sea, a body of liquid water that some estimates suggest could contain more than double the volume of all of Earth's oceans combined. This incredible reservoir of water remains in a liquid state, despite Europa's immense distance from the Sun and the frigid temperatures on its surface, not because of solar warmth. Instead, it's kept warm by a phenomenon known as tidal heating. Jupiter, being the most massive planet in our solar system, exerts powerful gravitational forces on its moon Europa. As Europa orbits, it's constantly stretched and squeezed by Jupiter's immense pull, much like a rubber ball being flexed. This continuous flexing generates immense friction and internal heat within Europa's core and mantle. This geothermal energy is sufficient to melt the deep ice, keeping the vast ocean beneath the surface in a liquid state. The moon's surface itself is a fascinating canvas, streaked with an intricate network of lines, ridges, and complex patterns. These surface features are not merely superficial, they are thought to be direct visual clues, hinting at the dynamic processes occurring in the hidden sea below. The shifting and cracking of the icy crust above this liquid ocean are believed to create these distinct geological markings. Scientists often envision a scenario where hydrothermal vents, similar to those found on Earth's ocean floor, might exist at the bottom of Europa's hidden sea. On Earth, these deep sea vents release superheated, mineral-rich water, creating unique ecosystems that thrive in complete darkness, fueled by chemosynthesis rather than sunlight. If such environments exist on Europa, they could provide the perfect conditions: warmth, water, and essential minerals to support the chemistry necessary for life to emerge. Although Europa's outer appearance is one of barren, desolate ice, it may, in its profound silence, conceal a vibrant world brimming with possibilities. It is widely considered one of the most promising locations in our solar system to potentially discover living organisms beyond our home planet. Saturn's largest moon, Titan, stands out as a truly remarkable celestial body. It is the only place in our solar system, apart from Earth, confirmed to host stable bodies of liquid on its surface. However, the chemistry there is profoundly different from our own world. Instead of flowing water, Titan's intricate network of rivers, expansive lakes, and vast seas are filled with liquid methane and ethane. Above this alien landscape, thick, hazy clouds drift through a dense atmosphere, and periodically rain falls, sculpting a terrain that bears an eerie, almost familiar resemblance to Earth's own geological features, but in an entirely alien chemical composition. Imagine standing on Titan's surface. The sky overhead would appear as a deep, muted orange, perpetually shrouded in a thick, nitrogen-rich atmosphere. The air would feel heavy and dense, pressing down with more force than Earth's atmosphere. Looking towards the horizon, you would see shimmering expanses of hydrocarbon seas, reflecting the dull, diffuse light filtering through the haze. Titan's peculiar hydrological cycle, driven by methane and ethane instead of water, creates weather patterns, seasons, and erosion processes that are strangely analogous to Earth's. Methane evaporates from the surface, rises to form clouds, precipitates as rain, and then flows across the land, carving channels and replenishing the liquid reservoirs. This continuous cycle not only shapes the moon's surface, but also hints at the potential for complex organic chemistry. Scientists are particularly interested in whether Titan's unique environment could be fostering chemical reactions similar to those that were critical for the initial spark of life on Earth billions of years ago. It presents a fascinating paradox: a world that is simultaneously familiar in its geological processes and utterly alien in its fundamental chemistry. Despite its extreme cold, Titan is a dynamic world featuring its own unique weather systems, distinct seasons, and landscapes meticulously carved by a liquid that is nothing like the water we know. It truly offers a singular window into an alternative form of planetary evolution. The diminutive moon Enceladus, another of Saturn's numerous companions, has emerged as one of the most captivating and intensely studied worlds in our solar system. Beneath its bright, icy crust lies compelling evidence of a vast, salty ocean. What makes Enceladus truly extraordinary, however, are the spectacular geysers that constantly erupt from deep fissures located near its south pole. These powerful fountains launch plumes of water vapor, fine ice crystals, and even complex organic molecules hundreds of miles into the frigid vacuum of space. The effect is dazzling, creating a visible, shimmering plume that can be observed even from afar by orbiting spacecraft. These geysers are incredibly potent, so much so, in fact, that the material they eject continuously feeds and helps shape Saturn's E-ring, forming a delicate, diffuse halo of particles that encircles the gas giant. This constant replenishment demonstrates a direct, dynamic link between the Moon and its planetary system. What is even more astonishing is the chemical composition of the material contained within these plumes. When the Cassini spacecraft, which spent years meticulously studying Saturn and its moons, made daring flybys directly through these erupting jets, it was able to taste their chemistry. The data collected revealed not just water, but also salts, silica, and a surprising array of organic compounds. This cocktail of ingredients strongly suggests that conditions within Enceladus's subsurface ocean could be remarkably hospitable for microbial life. The presence of liquid water, an energy source likely from hydrothermal activity on the ocean floor, similar to Europa, and essential organic building blocks, makes Enceladus a prime candidate in the search for extraterrestrial life. In those shimmering, constantly erupting jets, we catch a tantalizing glimpse of a hidden ocean world. A tiny moon that persistently announces its vibrant internal activity with spectacular, glittering sprays, broadcasting its secrets into the void for us to discover. Io, the innermost of Jupiter's 4 large Galilean moons, presents a stark contrast to its icy siblings. It is a world consumed by fire and intense geological activity. Its surface is extensively scarred by hundreds of active volcanoes, some of which are so powerful they launch molten fountains hundreds of miles high into the thin atmosphere. These eruptions dwarf anything observed on Earth, both in scale and frequency. The relentless volcanic activity on Io is fueled by the immense tidal forces exerted by Jupiter and its other large neighboring moons, Europa and Ganymede. As Io orbits Jupiter, it is constantly stretched and squeezed by the planet's powerful gravity. This immense gravitational flexing generates enormous internal friction, superheating Io's interior and keeping its core and mantle molten. This internal heat drives the moon's extreme volcanism. The entire crust of Io is in a state of perpetual flux and restlessness, constantly being reshaped and resurfaced by rivers of flowing lava. Because of this continuous geological upheaval, no two views of Io's surface are ever quite the same. New flows and eruptions perpetually alter its appearance. Standing on Io's surface would be an utterly impossible and deadly endeavor. The moon has only a very thin atmosphere, offering no protection from the intense radiation belts of Jupiter, which would quickly prove fatal. The ground beneath one's feet would be a seething, shifting landscape of extreme heat and molten rock. Yet, despite its hostile nature, from a distance, Io is a dazzling spectacle. It glows with the fiery energy of a world caught in a perpetual state of upheaval, a living furnace endlessly churning in orbit around the colossal gas giant, Jupiter. Its dramatic appearance is a vivid testament to the raw power of gravitational interactions in our solar system. Ganymede not only holds the title for the largest moon in our entire solar system, but also possesses a truly unique characteristic: it generates its own magnetic field. This is an extraordinary distinction, as even a full-fledged planet like Mercury cannot claim to produce its own internal magnetic field. The existence of this intrinsic magnetic field strongly suggests that Ganymede harbors a molten metallic core deep within its interior, similar to Earth's own dynamic core. This molten iron core, churning and circulating, creates a geomagnetic dynamo effect, generating the Moon's magnetic shield. Surrounding Ganymede is a very thin atmosphere, primarily composed of oxygen, a product of sunlight breaking apart water ice on its surface. The Moon's frozen surface is a complex mosaic, extensively scarred by countless impact craters, but also marked by mysterious, intricate grooves and ridges that hint at past geological activity. Ganymede is so massive that if it were orbiting the Sun directly instead of Jupiter, astronomers would almost certainly classify it as a planet. Its sheer size and internal dynamics blur the traditional distinction between moons and planets. Yet, Ganymede remains steadfastly a moon, eternally circling Jupiter, its colossal parent. In its orbit, it carries with it profound secrets of geology and magnetism, challenging our conventional definitions of what a moon can be. Its complex internal structure, including the magnetic field, suggests a world with its own independent geological evolution, not merely a passive companion. When we contemplate Ganymede, we are reminded that moons are far from being simple, inert satellites. They can be incredibly complex, active, and dynamic worlds, possessing features and processes as intricate and profound as those found on planets themselves. Its existence broadens our understanding of the incredible diversity present within our solar system. Beyond its role as the radiant beacon in our night sky, Earth's moon performs a much more fundamental service. For our planet, it acts as a crucial stabilizer for Earth's axial tilt. Our planet is tilted at approximately 23.5 degrees relative to its orbital plane around the Sun. This tilt is what gives us our distinct seasons, as different parts of the Earth receive more direct sunlight at various times of the year. Without the steady, gravitational pull of our moon, Earth's axis would not be nearly as stable. Instead, it would likely wobble chaotically, swinging dramatically between extreme angles. Consider Mars, for example, which lacks a large, stabilizing moon. Its axial tilt has undergone significant and rapid shifts over geological time, leading to drastic climate changes, oscillating between periods of intense ice ages and scorching hot summers. Such unpredictable and extreme instability in Earth's axial tilt could have made the long-term evolution and sustained existence of life, as we know it, an impossible feat. Furthermore, the moon's gravitational influence isn't limited to stabilizing our planet's orientation. It also stirs our vast oceans, creating the rhythmic ebb and flow of tides. These tidal forces are thought to have played a vital role in the early stages of life on Earth. The constant mixing and receding of waters in ancient tide pools could have created unique environments where complex organic molecules could accumulate, interact, and eventually form the first self-replicating structures, nurturing the chemistry that led to the very first living organisms. In this profound sense, our moon is much more than a mere celestial companion. It is an indispensable guardian. Its persistent, subtle presence has meticulously shaped Earth into the stable, life-friendly home that it is today. When we gaze upon it now, softly glowing above us, It's a humbling experience to realize that its quiet, unwavering influence may have been absolutely essential to our very own existence. It is a silent partner in the grand story of life. The prevailing scientific explanation for the origin of our moon is as dramatic as it is violent, a colossal event that reshaped both Earth and its future companion. The leading hypothesis, known as the giant impact hypothesis, suggests that approximately 4.5 billion years ago, in the chaotic early days of our solar system, a Mars-sized body, often nicknamed Theia, collided catastrophically with the young, still forming Earth. This wasn't a glancing blow, but a powerful, oblique impact that obliterated Theia and blasted an immense amount of molten rock, vaporized material, and debris into orbit around our nascent planet. This ejected material, now circling Earth, gradually began to coalesce and clump together under its own gravity. Over a period of possibly just a few thousand years, this orbiting debris slowly but surely gathered, fusing into the single, large satellite that would become our moon. Lingering evidence of this cataclysmic event persists even today. Scientists have found that Earth and the Moon share remarkably similar chemical and isotopic compositions, particularly in certain elements like oxygen. This striking chemical resemblance strongly suggests that both bodies were born from the same primordial material, lending powerful support to the idea that the Moon is essentially a fragment of the early Earth and the impacting body. The immense energy released during this collision likely had profound effects on Earth itself. It's believed that the impact might have been responsible for giving Earth its current axial tilt, setting the stage for the seasons we experience. It could also have increased Earth's rotation rate. What appears to us as a serene, timeless presence in the night sky is, in reality, the direct product of unimaginable fire and cosmic chaos. The Moon stands as a silent, luminous scar from Earth's early, turbulent history, a colossal impact event that ultimately forged its most faithful and influential companion. It's a powerful testament to the universe's capacity for both destruction and creation. From our vantage point on Earth, we always perceive the same face of the Moon. This is due to a phenomenon called tidal locking, where the Moon's rotation period perfectly matches its orbital period around our planet. Consequently, the side we see, known as the near side, is very different from the side that perpetually faces away from us, the far side. The contrast between these two lunar hemispheres is quite striking. The near side is predominantly marked by vast, dark, relatively smooth plains. These dark regions are called maria, which is Latin for seas, a name given by early astronomers who mistook them for actual bodies of water. These maria are, in fact, immense basins formed by ancient impacts that were later filled with dark, basaltic lava flows, solidifying into the flat landscapes we observe. In stark contrast, the far side of the Moon is almost entirely devoid of these dark maria. Instead, it is dominated by rugged, heavily cratered highlands and a much thicker crust. The terrain there is far more mountainous and pockmarked, a testament to billions of years of impacts without the resurfacing lava flows that characterize the near side. Scientists believe this dramatic difference is primarily due to uneven heating in the Moon's early history. It's thought that the near side experienced more intense and prolonged heating, possibly due to tidal interactions with Earth or a thinner crust, which allowed molten rock to well up and fill the basins, creating the maria. For the vast majority of human history, the far side of the Moon remained an utter mystery, completely hidden from our view. It wasn't until the dawn of the space age, specifically with the Soviet Luna 3 spacecraft in 1959, that humanity finally received its first images of this previously unseen hemisphere. Seeing those initial pictures was a groundbreaking moment, akin to discovering a completely separate moon, one that had been silently turning just out of sight for eons, finally revealing its starkly different, ancient face. It truly was like uncovering a hidden world. Triton, Neptune's largest and most intriguing moon, exhibits a truly peculiar behavior that sets it apart from almost every other large moon in our solar system. Most moons orbit their parent planets in the same direction that the planet spins, a prograde orbit. Triton, however, does the exact opposite. It circles Neptune in a retrograde orbit, moving in the direction opposite to Neptune's rotation. This unusual, backward path is a strong indicator that Triton did not form in situ around Neptune, alongside the planet's other original satellites. Instead, the scientific consensus is that Triton was likely captured from elsewhere in the solar system, perhaps once a free, floating dwarf planet originating from the distant Kuiper Belt, a vast region of icy bodies beyond Neptune. The capture of such a massive object like Triton would have been an incredibly violent and disruptive event. It would have dramatically destabilized Neptune's original system of moons, likely scattering them into new, eccentric orbits or even ejecting them from the system entirely. Some may have even collided and been destroyed during this chaotic period. Today, Triton remains a cosmic oddball, distinctive in its appearance and activity. Its surface is primarily composed of nitrogen ice, giving it a pale, almost pristine appearance. Despite its frigid temperatures, Voyager 2 discovered active geysers on Triton, spewing plumes of nitrogen gas and dust high into its thin atmosphere, leaving dark streaks across its icy plains. These geysers indicate that Triton is still geologically active, a surprising trait for a moon so far from the Sun. However, Triton's unique, backward orbit also carries a grim prognosis for its distant future. Neptune's immense gravity is slowly, but relentlessly dragging Triton inward, causing its orbit to decay over billions of years. Eventually, this process may lead to a catastrophic end. Triton could either plunge into Neptune's atmosphere or, more likely, it will cross a critical distance known as the Roche limit. At that point, Neptune's tidal forces will overpower Triton's own gravity, tearing the moon apart into countless fragments. These shattered pieces would then spread out, forming a magnificent and dramatic new ring system around Neptune, a cosmic farewell to a captured wanderer. It's a stark reality that moons orbiting too close to their parent planets exist in a constant state of gravitational peril. Their existence is precarious, subject to the immense stretching and pulling forces exerted by the planet's gravity. If a moon ventures inside a critical boundary, an invisible line in space known as the Roche limit, it can face a truly catastrophic fate. Within this specific distance, the planet's gravity exerts a stronger pull on the side of the moon facing the planet than it does on the far side. This differential gravitational force, known as tidal stress, effectively stretches and elongates the moon. If these tidal forces become more powerful than the moon's own internal gravity, which holds its material together, the moon can be torn apart entirely, disintegrating into a vast cloud of rubble. Scientists theorize that Mars's tiny moon Phobos is slowly, but inexorably spiraling inward towards the red planet. In the very distant future, perhaps in tens of millions of years, Phobos is predicted to meet this exact destiny. It could shatter into a spectacular field of debris, forming a temporary, diffuse ring around Mars before eventually raining down onto the planet's surface. This potential future for Phobos serves as a powerful reminder of the intricate and often violent connection between moons and rings. It highlights the dynamic nature of planetary systems, where one celestial body can transform into another. In the early, chaotic days of our solar system, it's possible that some magnificent ring systems, like those around Saturn, may have gradually coalesced and clumped together to form moons. Conversely, other moons, like the potential fate of Phobos, were torn apart by immense tidal forces, their shattered remnants contributing to the formation or replenishment of existing rings. These ongoing cosmic cycles vividly demonstrate just how dynamic and surprisingly fragile orbital mechanics truly are. While the celestial dance of moons and planets might appear timeless and unchanging from our human perspective, in reality, it's a constant process of transformation, destruction, and creation unfolding over immense geological timescales. Each orbiting body is part of a grand, cosmic ballet with a constantly evolving choreography. Pluto, the distant dwarf planet, shares a truly extraordinary relationship with its largest moon, Charon. This partnership is so unique that the two bodies are often described not merely as a planet and its moon, but rather as a double dwarf planet system. What makes them so distinct is the relative size of Charon compared to Pluto. Charon is remarkably large, approximately half the diameter of Pluto itself. This size ratio is highly unusual in our solar system. In most planet-moon systems, such as Earth and its moon, the smaller satellite clearly orbits around the larger primary body, with the center of mass lying well within the planet. However, with Pluto and Charon, this dynamic is fundamentally different. Both Pluto and Charon actually orbit around a shared center of mass, a point in space known as the barycenter, which lies outside of Pluto's surface. It's as if they are dancing around an invisible spot between them. Charon's surface itself is a fascinating landscape, scarred by enormous canyons and towering cliffs, some of which stretch for hundreds of miles. These geological features hint at a complex and active past, possibly involving internal expansion and contraction. This unusual, almost equitable partnership between Pluto and Charon blurs the conventional definitions that distinguish a moon from a planet. It shows us that in certain extreme cases, gravitational forces can bind two worlds into a more symmetrical and interdependent dance, rather than a clear hierarchical orbit of one around the other. If you were to visualize them in motion, it wouldn't be like a planet with a small companion revolving around it. Instead, it would appear more like two distinct celestial partners, forever turning and pirouetting together in the profound darkness of the outer solar system, locked in a unique and captivating gravitational embrace. Their dual nature challenges our perceptions of planetary systems and showcases the incredible diversity of orbital relationships possible in the cosmos. Miranda, one of the smaller, inner moons of Uranus, presents an astonishing and perplexing appearance. Its surface looks strikingly like a cosmic patchwork, as if a celestial body was shattered into numerous fragments and then somehow haphazardly stitched back together. The terrain is a chaotic jumble of dramatic cliffs, deep valleys, and prominent ridges, some of which tower to heights far exceeding Earth's Grand Canyon. This bizarre, mismatched landscape is a key piece of evidence supporting a fascinating scientific theory that Miranda may have indeed suffered a catastrophic collision with another large body in its distant past. Such an impact would have completely fragmented the moon. However, its own gravity would then have slowly, inexorably pulled the shattered pieces back together, reassembling them into the jumbled, fractured world we see today. This reassembly process would naturally explain its strange, varied terrain, where one region might look entirely different, almost alien, compared to an adjacent area. The most striking geological feature on Miranda is undoubtedly Verona Rupes, an immense cliff that holds the record for being the tallest known cliff in our entire solar system. Estimates suggest this colossal escarpment could be as high as 12 miles from its base to its summit. To put that into perspective, if you were to somehow fall from its dizzying edge, it would take a staggering 10 minutes to reach the bottom, plummeting through a vacuum. Verona Rupes is a monumental testament to the immense forces that shaped this tiny moon. Miranda, with its fragmented appearance and towering scars, feels like a world that has endured profound cosmic trauma. It is a resilient survivor, silently orbiting in Uranus's uniquely tilted realm, a constant reminder of the violent, creative, and reconstructive power of celestial collisions and gravity's relentless grip. Its very existence is a compelling story of destruction and rebirth. Phobos, the larger of Mars's two diminutive moons, is on a collision course with destiny, slowly spiraling towards its inevitable doom. With each successive orbit around the red planet, this small moon creeps imperceptibly closer to its parent body, shortening its orbital distance by approximately 7 feet every 100 years. While this might seem like an incredibly slow pace, over the immense timescales of celestial mechanics, it signifies a countdown. In roughly 50 million years from now, Mars's relentless gravitational pull will seal Phobos's fate. The moon will either be torn apart by the planet's gravitational pull. This massive pull will either completely tear it apart, transforming it into a dazzling but temporary ring of debris around Mars, or it will drag the moon down to a fiery collision with the planet's surface. Either way, Phobos faces an irreversible end. Today, if you were to look closely at images of Phobos, you'd see its surface is already covered in a network of long, shallow grooves and distinct cracks. Scientists believe these aren't just random marks from impacts. Instead, they are very likely early indicators of the immense stress that Mars's gravity is already placing on its moon. These fractures are the visible symptoms of Phobos slowly succumbing to the relentless tidal forces. Phobos itself is a relatively small body, only about 14 miles across at its widest point. Yet, its impending fate casts a huge shadow over its existence. To imagine the Martian sky without the swift passage of Phobos is to truly grasp that even moons, which seem like permanent fixtures in the cosmos, are merely temporary companions. Their orbits are often delicate, their futures always uncertain, shaped by the immense forces of gravity and time. The grooves we observe are like premonitions etched into its very being, a silent record of its approaching destruction. It's a powerful reminder of how dynamic and ever-changing even seemingly stable celestial relationships can be. A small moon, silently bearing the marks of its own eventual demise, circling its parent planet on a slow, one-way journey. Despite its serene appearance, the moon, our celestial neighbor, is not entirely silent or still. It experiences what scientists call moonquakes. When the Apollo astronauts visited the lunar surface, they left behind sensitive instruments called seismometers. These devices were designed to detect ground vibrations, similar to how we measure earthquakes on Earth. And to everyone's surprise, these seismometers revealed that the moon occasionally trembles. These moonquakes are not as frequent or as powerful as Earth's earthquakes, but they are a definite sign of internal activity. The causes of these lunar tremors are varied. Some are directly linked to the steady, gravitational tug of Earth. As our planet's gravity stretches and squeezes the moon, it creates tidal stresses within its interior, which can build up and then release, causing shallow quakes. Another type of moonquake is triggered by dramatic temperature shifts. The moon's surface experiences extreme temperature variations. During the long lunar night, temperatures plummet to incredibly frigid levels. But when sunlight returns, the lunar crust rapidly warms. This sudden and uneven heating can cause the rigid rock to expand and contract, leading to cracks and producing shallow tremors. These are known as thermal quakes. Then, there are deeper, stranger quakes that originate far beneath the lunar surface, deep within the moon's mantle. The exact origins of these deep moonquakes are still not entirely understood, posing an ongoing mystery for lunar scientists. What's particularly intriguing about moonquakes is how long their vibrations last. Unlike on Earth, where our planet's wetter, more ductile crust tends to dampen seismic waves relatively quickly, the moon's crust is extremely dry and rigid. This means that once a moonquake occurs, The vibrations can echo through the lunar interior for hours, causing the entire moon to literally ring like a bell. This eerie phenomenon provided invaluable data to scientists, allowing them to probe the moon's internal structure in detail. While the moon doesn't have plate tectonics like Earth, meaning its crust isn't broken into moving plates, its interior is certainly not entirely quiet. Each moonquake serves as a subtle, yet powerful reminder that beneath its calm, ancient surface, our moon remains alive with hidden, geological energies. Scattered across the moon's dusty surface are countless tiny, almost invisible glass beads. These microscopic spheres weren't placed there by some alien hand. They were formed billions of years ago during intense volcanic eruptions. When molten rock was violently ejected from the moon's interior, it cooled incredibly rapidly as it flew through the vacuum of space, solidifying into these perfect, glassy orbs before hitting the ground. Recently, scientists made a truly remarkable discovery about these seemingly ordinary beads. They contain water, locked away within their glassy structures. This finding was a game changer because, for a long time, the moon was largely considered to be a bone, dry, parched world, utterly devoid of any significant water reserves. The presence of water within these ancient glass beads completely reshapes that perception. While each individual bead holds only a minuscule amount of moisture, when you consider the sheer number of these beads scattered across the vast lunar landscape, they represent a potentially enormous reservoir of hidden water. This discovery means that the moon is not just a barren desert, but a place with significant resources quietly waiting beneath its dust. For future human explorers, this has incredibly exciting implications. Such beads could potentially be harvested and processed to extract the trapped water. This water could then be used for drinking, sustaining life in future lunar outposts, or even broken down into its constituent elements hydrogen and oxygen. Hydrogen and oxygen are the primary components of rocket fuel, meaning these microscopic spheres could provide a vital, in situ fuel source for missions venturing further into the solar system. The discovery truly transformed our understanding of the moon. It's no longer just a desolate rock, but a world with valuable resources, quietly preserving traces of its fiery past within each small bead, and perhaps holding a key to its future as an essential stepping stone for humanity's journey beyond Earth. When the Apollo astronauts returned to their lunar modules after their historic walks on the moon, they immediately noticed something very distinct. The fine, gray dust that covered the lunar surface clung tenaciously to their spacesuits and boots. Once inside the cabin, as they took off their helmets and the dust became airborne, it permeated the air and carried a very particular smell. Every astronaut described it similarly, like burnt gunpowder, or perhaps a faint scent of metallic ozone. This lunar dust, officially known as regolith, is unlike any dust found on Earth. It's not smooth or soft like beach sand. Instead, it's composed of incredibly tiny, jagged shards of rock and glass. These fragments were created over billions of years by the relentless bombardment of the moon's surface by countless meteorites. Each impact shattered and pulverized the lunar rocks, grinding them down into these incredibly abrasive, sharp, edged particles. Because the moon has no atmosphere, there's no wind, no water, no geological processes like erosion to wear down these sharp edges. So, the regolith remains perpetually jagged and abrasive. This characteristic made it a real nuisance for the astronauts. The dust clung everywhere due to electrostatic forces. It wore holes in the tough fabric of their spacesuits, and it clogged mechanical equipment, proving to be a serious engineering challenge. More worryingly, its extremely fine, sharp particles meant that breathing it in could be dangerous, potentially lodging deep within the lungs and causing respiratory problems. To the astronauts, that first distinct whiff of the lunar dust was an experience that was both profoundly strange and utterly unforgettable. It was the unique scent of an entirely different world, a place that has no air, no rain, and no life, yet manages to leave its distinct mark in the sharpest and most unexpected of ways. It was the smell of cosmic history, clinging to their very suits. The astronauts who journeyed to the moon during the Apollo missions did more than just walk on its surface. They established a series of groundbreaking scientific experiments. Many of these instruments were designed to operate autonomously and continued to gather valuable data for decades after the human explorers departed. One particularly enduring experiment involved placing special mirrors, known as retroreflectors, on the lunar surface. These mirrors are still in use today. Scientists on Earth regularly aim powerful lasers at these retroreflectors. By precisely measuring the time it takes for the laser light to travel from Earth, bounce off the mirrors on the moon, and return, they can determine the exact distance to the moon with incredible accuracy. These ongoing measurements have been instrumental in confirming a crucial astronomical fact, that our moon is indeed slowly, but steadily drifting away from Earth a tiny bit farther each year. Other scientific packages left by the Apollo crews provided deep insights into the moon's internal structure and its surrounding environment. Seismometers, as we mentioned, detected moonquakes, revealing details about the moon's interior composition. Magnetometers measured the moon's magnetic properties, and heat flow experiments studied its internal temperature. These instruments continued to provide a steady stream of data long after the astronauts had departed, extending the scientific legacy of the Apollo missions for many years. Even now, the quiet, ancient moon carries these silent reminders of those brief human visits. These instruments, gathering knowledge in the profound darkness of space, act as a continuous link, connecting Earth and its moon with invisible beams of light and streams of data. They are quiet sentinels, forever watching and measuring. Callisto, Jupiter's second largest moon, appears, at first glance, to be one of the most geologically inactive and ancient worlds in our solar system. Its surface is absolutely covered in craters, more so than almost any other body we've observed. This heavily pockmarked appearance makes it seem like a frozen record of the solar system's earliest, most violent days, a world entirely unchanged for billions of years. However, despite this seemingly dead exterior, scientific measurements and observations have hinted at something truly surprising lurking beneath its ancient crust. Callisto may conceal a vast, salty ocean. If this hidden ocean truly exists, it would mean that liquid water has been preserved within Callisto for an incredible amount of time, perhaps billions of years, quietly enduring while the surface above has remained largely unaltered. Unlike Europa's constantly shifting, restless ice or O's fiery volcanic chaos, Callisto presents a picture of profound stillness and ancient stability. Its potential hidden sea, sealed away beneath layers of ice and rock, could be nearly as old as the solar system itself. This makes Callisto a fascinating study in cosmic endurance. In its profound silence, this seemingly barren moon could hold secrets of stability, survival, and the long-term persistence of liquid water in the extremely cold, outer reaches of space. It challenges our assumptions about what makes a world active or alive, suggesting that life, if it were to exist there, would be deeply insulated, thriving in a primordial sea untouched by the surface's harsh environment. Callisto, in its quiet, cratered grandeur, offers a unique window into the deep past and the hidden potential of distant, icy worlds. Apetus, one of Saturn's more enigmatic moons, possesses a truly striking and mysterious feature. It appears as though it's painted with a cosmic yin-yang symbol across its surface. One hemisphere gleams with an almost blinding brightness, as pure and white as freshly fallen snow, while the opposite side is stained and incredibly deep, almost velvety black, as dark as coal. This dramatic, two-toned appearance has baffled astronomers for centuries, leading to much speculation and many theories. The most widely accepted explanation for this stark division involves dark dust originating from another of Saturn's moons, Phoebe. Phoebe, a small, dark, irregular moon orbiting much farther out from Saturn, is known to be covered in very dark, carbonaceous material. As Iapetus sweeps through space, it is thought to constantly encounter and accumulate this dark, dusty material from Phoebe, which then coats its leading hemisphere. Once this dark dust settles on one side of Iapetus, a feedback loop begins. The darkened areas absorb more sunlight, causing them to warm up. This warming, in turn, causes any ice on the dark surface to sublimate, turn directly from solid to gas, leaving behind an even higher concentration of dark material. This process makes the already darkened areas grow even darker, intensifying the sharp contrast we observe today. Iapetus also possesses another peculiar feature: a massive, inexplicable equatorial ridge that wraps around its middle, giving it the appearance of a walnut or a giant, cosmic pie crust. Few other moons in our solar system display such a bizarrely divided appearance, half brilliantly glowing and half profoundly shadowed. It stands as a silent, cosmic symbol, orbiting quietly in Saturn's vast and diverse domain, a testament to complex interactions between moons and their shared environment. Hyperion, another of Saturn's many moons, is undoubtedly one of the most peculiar and strangely beautiful objects discovered in our solar system. It is a small, irregularly shaped body, far from spherical, and its surface is riddled with deep, cavernous craters, giving it an unmistakable resemblance to a giant, tumbling sponge. But what makes Hyperion even more unique and captivating is its utterly unpredictable spin. Unlike most celestial bodies that rotate steadily and predictably around a fixed axis, Hyperion tumbles chaotically through space. It spins and wobbles erratically, as if it's constantly losing its balance, never quite settling into a stable rotation. No two observations of its rotational period or axis ever match exactly, highlighting the truly chaotic nature of its spin. This erratic behavior is due to its irregular shape and the complex gravitational tugs from Saturn and its other moons, which prevent it from settling into a tidally locked or stable rotation. Adding to its mystery, Hyperion possesses an unusually low density. This suggests that the moon is incredibly porous, much like a pile of rubble or a cosmic Swiss cheese, with vast empty spaces within its structure. It's barely held together by its own weak gravity. This combination of chaotic tumbling and fragile, porous composition makes Hyperion both scientifically fascinating and visually unique. It truly is a cosmic sponge, adrift in Saturn's vast orbit, forever tumbling in an unpredictable, yet mesmerizing, dance through the void. It's a testament to the sheer diversity of objects that can exist even within a single planetary system. Auroras, those mesmerizing, shimmering curtains of light that dance across the polar skies, aren't exclusively limited to planets. Some moons, particularly those immersed within a planet's powerful magnetic field, can also glow with their own spectacular displays of light. Ganymede, Jupiter's colossal moon, is a prime example. As the only moon known to possess its own internally generated magnetic field, it interacts with Jupiter's even larger magnetosphere. This interaction causes charged particles from Jupiter's magnetic environment to funnel towards Ganymede's poles, exciting atmospheric gases and creating vibrant auroras that ripple and shimmer across its polar regions. But even moons without an intrinsic magnetic field can sometimes sparkle with light. Their thin atmospheres, or even their bare surfaces, can be illuminated by streams of charged particles racing through space, creating a faint, ethereal glow. While these lunar auroras may not always be visible directly to the human eye, advanced spacecraft instruments are capable of capturing their subtle brilliance. The very idea of a distant moon, silent and seemingly airless, being crowned with an invisible storm's light, is profoundly evocative and a little haunting. It serves as a powerful reminder that space is not merely an empty void, but is alive with unseen energies and dynamic interactions, constantly painting even the smallest worlds with unexpected and beautiful colors. These lunar light shows reveal the complex interplay between moons, their parent planets, and the powerful magnetic fields that envelop them, turning remote celestial bodies into canvases for cosmic artistry. It might seem counterintuitive that moons, far from the Sun, existing in the frigid outer reaches of the solar system, could harbor liquid water. Logic would suggest they should be frozen solid, from surface to core. Yet, many of these distant satellites are believed to conceal vast, subsurface oceans beneath their icy crusts. The secret to these hidden seas lies in a process called tidal heating. As a moon orbits a massive planet, it is continuously subjected to immense gravitational forces. These forces cause the moon to be stretched and squeezed, much like kneading dough. This constant flexing generates enormous amounts of friction and internal heat deep within the moon's interior. This warmth is often sufficient to melt the deep ice, keeping substantial bodies of water in a liquid state, even under miles of overlying ice. Europa and Enceladus are the most well-known examples, both with strong evidence for global subsurface oceans. But possibly Callisto, and even Titan with its water, ice mantle beneath its hydrocarbon layers, may also possess such hidden reservoirs. These underground seas are considered some of the most promising locations in our solar system to search for extraterrestrial life. Shielded from the harsh radiation and extreme temperatures of space by thick icy shells, these environments could provide the stability, liquid water, and chemical energy necessary for life to emerge and thrive. Beneath apparently barren surfaces, entire oceans may be stirring, kept alive by nothing more than the steady, rhythmic pull of gravity. It is a testament to the diverse ways life, supporting conditions can arise in the cosmos. It sounds almost impossible, but Saturn's largest moon, Titan, boasts an atmosphere that is actually denser and thicker than Earth's own atmosphere. Its skies are perpetually filled with a rich mixture of nitrogen gas, much like Earth's air, but also a complex, thick haze of organic molecules. If you could stand on Titan's surface, the atmospheric pressure would feel significantly heavier than the air pressure does here on Earth, pressing down with greater force. This remarkably thick atmosphere is what allows for a complete, Earth-like weather system to exist on Titan. It supports the formation of clouds, drives powerful winds that sculpt the landscape, and allows for the precipitation of rain, though, of course, it's liquid methane and ethane that falls from its skies. While Earth's moon possesses only an incredibly tenuous exosphere, a mere trace of gas, Titan's dense, hazy skies strikingly resemble what scientists believe Earth's atmosphere might have been like in its very early stages, billions of years ago, before life profoundly altered its composition. It offers a unique, frozen snapshot of a primordial planetary environment. This characteristic serves as a powerful reminder that moons are not merely small, inert companions to planets. They can, in fact, possess environments as rich, complex, and dynamic as those found on planets themselves, challenging our preconceived notions of what a moon can be. Titan truly stands as a fascinating example of planetary evolution playing out on a satellite. Saturn's tiny moonpan is perhaps one of the most uniquely shaped objects in our entire solar system. Its form is so bizarre and distinctive that it hardly seems natural. With a prominent, bulging equatorial ridge running all the way around its middle, it bears an uncanny resemblance to a flying saucer or, more whimsically, a piece of cosmic ravioli gracefully drifting through space. Pan's highly unusual shape isn't an accident, It's a direct result of its unique interaction with Saturn's magnificent rings. As Pan orbits within the Encke gap, a clear division in Saturn's A ring, it acts as a shepherd moon. It sweeps up loose ring material with its gravity, and over time, this collected debris has accumulated around its equator, gradually building up that distinctive ridge. Pan is incredibly small, measuring barely 20 miles across. Its sculpted appearance makes it look almost as if it were deliberately shaped by hand, rather than formed through natural geological processes. Yet, despite its diminutive size and playful appearance, Pan is far from an insignificant toy. It plays a crucial role in maintaining the integrity of Saturn's rings, actively carving and sustaining the Encke gap through its gravitational influence. This demonstrates that even the tiniest moons can exert a significant and remarkable influence on their surroundings, shaping and defining the vast, intricate structures of a planetary system in profound ways. Pan is a testament to the subtle but powerful interplay of gravity and matter in the cosmos. Mimas, another of Saturn's smaller, inner moons, gained widespread fame for its truly astonishing resemblance to the iconic Death Star battle station from the Star Wars saga. This uncanny similarity is primarily due to a colossal impact crater named Herschel, which dominates one entire hemisphere of Mimas. The crater is so vast, measuring about 80 miles across Ars, roughly 1/3 of Mimas's total diameter, and features a prominent central peak, giving the moon that eerie, familiar look of the fictional space station. However, despite its menacing appearance, Mimas is anything but. It is a cold, frozen, and heavily battered world, only about 250 miles across, a far cry from a superweapon. Its striking resemblance to the Death Star is, of course, a pure cosmic coincidence. Yet it has undeniably captured the imagination of almost everyone who has seen its image. For scientists, however, Mimas holds interest for reasons beyond its pop culture connection. Researchers are particularly intrigued by the possibility that its interior may not be entirely solid. Recent studies, based on Mimas's subtle wobble as it orbits Saturn, suggest that it could potentially hide a liquid ocean beneath its thick, icy crust. This would be a truly astonishing discovery for a moon of its size, as it was previously thought to be too small and too geologically inactive to sustain such a feature. If confirmed, this hidden ocean would transform Mimas from a familiar-looking frozen orb into a much deeper, more complex, and potentially life-bearing mystery. It shows how even the most outwardly simple celestial bodies can conceal profound secrets beneath their surfaces, challenging our initial perceptions. Amalthea, one of Jupiter's inner moons, is small and irregularly shaped, lacking the spherical symmetry of larger bodies. Despite its modest size, its landscape is characterized by extreme geological features. Its surface is scarred by towering mountains and deep valleys, some of which rise to heights greater than Earth's Mount Everest. This dramatic topography on such a small moon is quite remarkable. Amalthea also possesses a faint reddish glow, a coloration scientists believe is caused by sulfurous compounds deposited on its surface from the volcanic eruptions of its nearby neighbor, Io. Although Amalthea measures only about 100 miles in its longest dimension, it plays a subtle but important role in the Jovian system. It contributes dust particles to Jupiter's faint, gossamer rings, helping to feed and maintain these tenuous structures. Its dramatic, miniature terrain vividly demonstrates how even the smallest moons can possess grand features that rival those found on much larger planets, simply compressed into a more compact world. Amalthea may be tiny, but its impressive peaks and plunging valleys stand as a testament to the powerful forces and unique geological processes that can shape even the most minor celestial companions. It's a compelling example of how scale in the universe can be deceptive. Monumental landscapes can exist on worlds we might otherwise overlook. Himalaya is one of Jupiter's more enigmatic and strangely behaving moons, orbiting far beyond the planet's main retinue of large, regular satellites. It holds the distinction of being the largest member of a loose group of irregular satellites, often referred to as the Himalaya group. Unlike the well-behaved, orderly orbits of Jupiter's inner moons, Himalaya does not follow a neat, prograde path aligned with the planet's equator. Instead, it traces a highly tilted and eccentric, or elongated, orbit. This unusual orbital configuration strongly suggests that Himalaya did not form in place around Jupiter. Instead, scientists believe it is a captured asteroid, a wanderer from the outer solar system that was eventually pulled in by Jupiter's immense gravitational grasp and held captive. Himalaya measures approximately 100 miles across and has a dull, gray surface, which lacks the bright, icy sheen characteristic of Jupiter's inner moons like Europa or Ganymede. This darker, rocky composition further supports the theory of its asteroidal origin. Himalaya serves as compelling proof that Jupiter, with its overwhelming gravity, acts as a cosmic vacuum cleaner, constantly gathering stray objects and turning them into new, if sometimes temporary, moons. This process reshapes the overall population and dynamics of its vast moon system. It shows us unequivocally that not all moons are born alongside their parent planets. Some are travelers, cosmic drifters, that are eventually caught and kept forever in a planetary embrace. Their presence tells a story of dynamic encounters. While most moons in our solar system adhere to a predictable pattern, orbiting their parent planets in the same direction that the planet itself spins, a fascinating few defy this conventional order. These are known as retrograde moons, and they circle their planets in the opposite direction, essentially rebelling against the prevailing celestial flow. Neptune's colossal moon Triton is the most famous and largest example of such a retrograde orbiter, moving counter to its planet's rotation. However, many smaller, irregularly shaped captured moons around the giant planets also follow these backward paths. Their unusual orbits serve as strong evidence that they did not form concurrently with their planets from the same initial disk of gas and dust. Instead, they were likely captured much later in the solar system's history, pulled in by a planet's immense gravity after wandering through space as independent bodies. The process of capturing a moon can be incredibly violent and disruptive. Such an event could dramatically alter the planet's original moon system, potentially shattering or even ejecting existing moons. It might even affect the tilt of the planet's rotation axis. A backward orbit, therefore, is more than just a strange anomaly. It's a crucial clue, a physical fingerprint pointing to a turbulent and often dramatic past. It's a reminder that the solar system is a place of constant change, filled with chance encounters, powerful gravitational interactions, and dramatic captures that have fundamentally reshaped entire worlds and planetary systems into the configurations we observe today. These retrograde moons are like cosmic historians, silently revealing tales of ancient, chaotic events. Janus and Epimetheus, two tiny moons orbiting Saturn, engage in one of the most remarkable and delicate celestial ballads in our solar system. They share an incredibly close, almost identical orbit around the ringed giant. What's astonishing is that instead of colliding with each other, which seems inevitable given their proximity, they perform a graceful orbital swap every few years. Here's how it works: the inner moon, which is moving slightly faster, gradually catches up to the outer moon. Just as they are about to approach each other, their mutual gravitational attraction causes them to exchange orbital energy. This exchange results in the inner moon receiving a gravitational boost that pushes it into a slightly higher, slower orbit, while the outer moon loses a bit of energy, causing it to drop into a slightly lower, faster orbit. Essentially, they trade places. This intricate orbital dance repeats endlessly, a flawlessly choreographed rhythm dictated by gravity itself. The arrangement is incredibly rare and highlights how moons can achieve remarkable stability even in precarious orbital positions. It's a beautiful demonstration of gravitational resonance and cooperation. Observing Janus and Epimetheus is like watching two partners in a cosmic dance, perpetually trading steps around Saturn. They never collide, always moving in perfect harmony, a testament to the elegant solutions gravity can devise to maintain stability in a crowded planetary system. Their unique interaction is a masterclass in celestial mechanics. Many moons across our solar system are tidally locked, meaning they keep one face perpetually pointed towards their parent planet. For us, observing such a moon, it appears as though it doesn't rotate at all. However, technically, it does rotate, but its rotation period is exactly synchronized with its orbital period around its planet. Our own moon is the most familiar example of this phenomenon, which is why we always see the same lunar face. But beyond these tidally locked companions, some irregular moons exhibit an even more unusual rotational behavior. They spin so incredibly slowly that their rotation can take days or even weeks to complete a single turn. They appear almost frozen in their motion. This sluggish rotation is often a consequence of their irregular shapes and the complex, uneven gravitational tugs exerted by their parent planets and other nearby moons. These forces gradually dampen their spin, slowing them down over immense periods. Imagine standing on the surface of such a moon. The stars in the sky wouldn't streak by as they do from Earth. Instead, they would crawl across the celestial dome at an almost imperceptible pace. It might take an entire week to notice any significant shift in their positions. This extreme slowness serves as a profound reminder that the passage of time, or at least how we perceive celestial motion, unfolds very differently depending on where you happen to be positioned in our vast solar system. These slowly spinning moons are not just curiosities. They are silent witnesses to the subtle, long-term effects of gravitational forces, shaping the very rhythm and apparent motion of worlds in the cosmic dance. Earth's axial tilt, currently at about 23.5 degrees, is the fundamental reason we experience distinct seasons throughout the year. Without this tilt, the sun's rays would strike the equator more directly all year round, leading to far less variation in temperature and climate. The moon plays an absolutely vital role in maintaining this tilt. Its steady, persistent gravitational pull acts as a cosmic anchor, preventing Earth's axis from wobbling wildly. Without our large moon, Earth's axial tilt could experience chaotic shifts, swinging unpredictably between extreme angles. We can look to Mars as a comparison. Mars lacks a large stabilizing moon, and geological evidence shows that its axial tilt has undergone dramatic and irregular changes over its history, leading to periods of extreme climate variability. The moon's influence, by dampening these potential variations, has kept Earth's climate relatively stable for billions of years. This long-term stability is thought to have been absolutely crucial for the emergence, survival, and complex evolution of life on our planet. It provided ecosystems with the consistent conditions and extended periods of calm necessary to adapt and thrive without being subjected to sudden, planet-wide upheavals. The moon's influence, while quiet and largely invisible in our daily lives, is constant and profound. It truly acts as a cosmic anchor, steadfastly steadying Earth's delicate balance in the immense, ever-shifting vastness of space, making our world a more hospitable place for life. Long, long ago, in the very early history of our planet, Earth spun much faster than it does today. Imagine a time when a single day might have lasted only a mere 6 hours. However, over the immense stretch of billions of years, a subtle but relentless interaction with our moon has been gradually stretching out time itself. As the moon exerts its gravitational pull on Earth's vast oceans, it generates the familiar phenomenon of tides. These tidal bulges, as Earth spins beneath them, effectively transfer a tiny amount of rotational energy from our planet to the Moon's orbit. The direct consequence of this energy transfer is that Earth's rotation gradually slows down. This deceleration, in turn, makes each successive day slightly longer than the last. The effect is incredibly subtle on a human timescale. Today, we measure that approximately 1.7 milliseconds are added to the length of a day each century. This is so minute that it's entirely imperceptible in a single human lifetime. But when you extrapolate this effect over billions of years, the cumulative change becomes monumental. The length of a day that you experience right now is significantly different from what it was for the earliest forms of life on Earth. It's a profound thought. The Moon, simply by performing its graceful orbit around our planet, has been slowly but surely reshaping the fundamental rhythm of our world, subtly stretching time itself across the vast cosmic timeline. It's a testament to the Moon's enduring, quiet power. When you look at the dark, expansive patches on the Moon's surface with your naked eye, those broad, relatively smooth plains, you are actually observing ancient lava flows that have long since frozen in place. Billions of years ago, during a period of intense geological activity, the Moon's crust was repeatedly fractured by massive impacts from asteroids and comets. These colossal impacts created vast basins. In response, molten rock, superheated from the Moon's interior, welled up to the surface through these cracks. It then spread out, flowing across these immense basins to form what were essentially vast, glowing seas of liquid lava. These dark plains are known as Maria, a Latin word meaning seas, a term coined by early astronomers who, observing them from Earth, mistakenly believed they were actual bodies of water. Gradually, over millions of years, these molten Maria cooled and solidified, hardening into the dark, basaltic plains that are so prominently visible on the Moon's face today. To ancient observers, these features inspired countless myths and legends, often associated with bodies of water or shadows. But their true geological story is far more dramatic and awe-inspiring. The Moon, in its early, tumultuous history, once glowed with immense rivers and seas of fire. Its entire visible face was fundamentally remade by these molten tides, which then slowly hardened into the enduring dark marks that we still see each and every night. They are permanent scars, beautiful in their starkness, telling a story of fiery transformation. At the Moon's poles, there exist some craters whose interior floors lie in permanent, perpetual shadow. Due to the Moon's slight axial tilt, sunlight never, ever reaches the depths of these particular craters. Consequently, temperatures within these cold traps plummet to incredibly frigid levels, hundreds of degrees below 0 Fahrenheit. Within these perpetually dark and cold environments, water ice has accumulated over billions of years. This ice is believed to have been delivered to the Moon by countless comets and asteroids that impacted its surface throughout its history. Once deposited in these sunless depths, the water ice is locked away, untouched and preserved for eons, never sublimating back into gas because the temperatures are too low. For future human explorers and lunar missions, these icy reservoirs represent an incredibly valuable resource. The ice could be harvested and melted to provide drinking water, a vital necessity for any long-term lunar outpost. Furthermore, the water could be electrolyzed, a process that separates it into breathable oxygen for astronauts and hydrogen, which, as mentioned before, can be used as rocket fuel. The discovery of these significant amounts of lunar ice completely transformed our understanding and perception of the Moon. It's no longer just a barren, dry rock, but a world with crucial resources quietly waiting in its shadowed depths. In each of these frozen traps lies not only a record of the Moon's ancient bombardment, but also a key to its future as a practical and strategic stepping stone for humanity's expansion into the solar system. Even though our moon appears as a brilliant, luminous orb in the night sky, it is, in reality, surprisingly dark. Its surface actually reflects only a mere 12% of the sunlight that strikes it. To put that into perspective, the moon's surface is darker than a patch of worn asphalt on Earth. The illusion of its dazzling brightness comes simply from the dramatic contrast with the profound blackness of space surrounding it. If we were to place the moon directly alongside Earth in space, our lunar companion would appear as a dull, muted gray, looking quite dim compared to our vibrant blue and white planet, which reflects much more sunlight. This low reflectivity, a property known as albedo, is primarily due to the moon's dusty, basaltic soil, the same dark rock that makes up its maria. What appears to us as glowing silver, inspiring poets and artists for millennia, is actually just the faint, subtle gleam of a world that, despite its prominent place in our heavens, shines only dimly. Yet, this modest reflectivity is more than sufficient to beautifully light our nights, guide our way, and continue to inspire our imaginations with its quiet, understated presence. Its dimness is a fundamental characteristic that speaks to its geological composition and surface properties. The moon is a master of illusion, a testament to how perception can be shaped by context, appearing brilliant against the void despite its inherently dark nature. Lunar soil is not soft and yielding like the sandy beaches or rich topsoil we find on Earth. It has a profoundly different and much harsher character. It is composed of incredibly tiny, sharp, edged grains, which were formed over billions of years by the ceaseless impact of meteorites. Each impact shatters lunar rocks into countless glassy fragments. Crucially, on the moon, there is no wind, no flowing water, and no significant atmospheric erosion to wear down these sharp edges and smooth out the particles. Consequently, the lunar dust, or regolith, remains perpetually jagged and abrasive, feeling more like tiny shards of glass than ordinary soil. Apollo astronauts quickly discovered the challenging nature of this dust. It clung tenaciously to everything due to electrostatic charges. It was so abrasive it wore down the seals on their equipment, scratched their helmet visors, and even cut through the durable fabric of their spacesuits. Breathing this fine, sharp particulate matter would be incredibly dangerous, as its tiny, jagged particles could easily lodge deep within the lungs, causing serious health issues. To walk on the moon, therefore, is not to stroll across a gentle landscape, but to navigate a field of countless, invisible tiny knives. The dust itself is both a fascinating historical record, preserving the evidence of billions of years of cosmic impacts, and a formidable challenge for any future human missions that will inevitably return to its surface. Its unique properties are a direct consequence of the moon's airless, waterless environment, making it a harsh, alien substance unlike anything we commonly encounter on Earth. This abrasive dust is a constant reminder of the moon's ancient, violent past and the difficulties it poses for exploration. The gravitational pull of the moon doesn't just create the spectacular ebb and flow of tides in Earth's vast oceans. Its influence extends far deeper, subtly stretching the solid Earth itself. Our planet experiences a slight bulge in the direction of the moon, making Earth ever so subtly egg-shaped, rather than a perfect sphere. This effect is incredibly tiny, completely imperceptible without highly precise scientific instruments, but it serves as a powerful reminder of just how profoundly and pervasively the moon influences our world. Its gravity penetrates through the entire planet, through solid rock, through liquid water, and through the enveloping atmosphere, exerting a gentle but persistent tug on every part of Earth. Our planet and its moon are locked in a continuous, complex gravitational embrace, silently shaping one another in ways we rarely notice in our daily lives. Yet, These subtle interactions ripple across the entire Earth-Moon system, influencing everything from the planet's rotation to its internal dynamics. It's a cosmic dance where two bodies are forever bound, constantly deforming and responding to each other's presence. This subtle egg-shaped deformation is a testament to the immense, far-reaching power of gravity, demonstrating that even what seems like a rigid, unyielding planet is constantly molded by the forces of its orbiting companion. It's a hidden layer of interaction in our celestial partnership. A moon that ventures too close to its parent planet faces an existential threat. If it crosses a specific, critical boundary in space, known as the Roche limit, the immense gravitational forces of the planet can literally tear the moon apart. Within this perilous distance, the planet's gravity exerts a significantly stronger pull on the side of the moon closest to it than it does on the side facing away. This differential gravitational force creates an intense stretching effect on the moon's body. If these tidal forces, which are essentially stretching the moon, become stronger than the moon's own internal gravity, which is what holds its material together, the moon can shatter completely. It will disintegrate into countless fragments. Astronomers widely believe that Saturn's spectacular and iconic rings may have originated precisely in this manner. A moon, or perhaps several moons, wandered too close to the gas giant in the distant past and were ripped into pieces by its overwhelming gravity. These shattered remnants then spread out, forming the magnificent, glittering ring system we admire today. In the far distant future, Mars's small moon Phobos is predicted to meet this very same fate, slowly being torn into a field of rubble. The very idea that a solid, once whole world can unravel and transform into countless, tiny fragments is a powerful illustration of how fragile even moons can be when subjected to the immense, relentless gravitational grip of their parent planets. It shows a universe where destruction can often lead to new, breathtaking formations. Many moons in our solar system exist in a state known as tidal locking, a perfect gravitational rhythm where they consistently present the same face to their parent planet. Our own moon is the most prominent and familiar example of this phenomenon. It rotates exactly once on its axis in precisely the same amount of time it takes to complete one orbit around Earth. This precise synchronization is why, from our perspective, we always see the same side of the moon. Tidal locking is not an instantaneous event, it occurs gradually over immense periods. The gravitational forces between a planet and its moon create bulges on the moon's surface. The planet's gravity then tugs on these bulges, slowly acting as a brake, gradually slowing down the moon's rotation until it perfectly matches its orbital period. The result is a kind of exquisite gravitational rhythm, a delicate balance that feels almost like a perpetual dance. While it means that one hemisphere of the moon is forever hidden from its planet, it also creates a remarkable stability within these planetary systems. Moons locked in this eternal, synchronized turn beautifully demonstrate how the powerful, pervasive force of gravity can sculpt both time and motion into a profound state of cosmic harmony. It's a testament to the intricate and elegant mechanics that govern celestial bodies, a silent, rhythmic ballet unfolding across billions of years. Not all orbital paths are immutable or fixed forever in the cosmos. Some unique pairs of moons actually engage in a delicate gravitational exchange, periodically swapping their orbital positions with each other. Saturn's tiny moons, Janus and Epimetheus, offer the best known and most captivating example of this celestial phenomenon. These two small satellites orbit Saturn in incredibly close proximity, following nearly the same path. Every few years, as the inner moon, moving slightly faster, begins to catch up to the outer moon, something remarkable happens. Instead of colliding, their mutual gravitational attraction causes them to exchange orbital energy. This exchange means the inner moon gets a slight gravitational boost, nudging it into a slightly higher, and thus slower orbit. Simultaneously, the outer moon loses a bit of energy, causing it to drop into a slightly lower, and thus faster orbit. They essentially trade places. This intricate, cosmic switch has been repeating flawlessly for millions of years, an astonishingly precise and graceful balancing act choreographed by gravity itself. It vividly illustrates how even tiny moons can interact and cooperate in surprisingly complex ways, finding a dynamic form of stability through their perpetual motion. Observing Janus and Epimetheus as they trade positions is like witnessing gravity write a beautiful, intricate choreography across the heavens, a continuous, elegant dance performed around the ringed giant. It's a compelling example of orbital mechanics achieving a stable, yet ever-changing equilibrium. The moon's gravitational influence extends beyond the visible tides in our oceans. It also subtly tugs and deforms Earth's solid crust. This constant pulling creates what are known as body tides within the Earth itself. The stress generated by these lunar tides can, under certain circumstances, play a role in triggering earthquakes or influencing volcanic eruptions, particularly in regions that are already geologically active and primed for such events. Scientists refer to these as tidal stresses. While these stresses don't directly cause major quakes or eruptions on their own, they can act as a subtle nudge, providing the final push that triggers activity along fault lines or within magma chambers at just the right, critical moment. It's truly astonishing to contemplate that our moon, situated so far away, can have a tangible, albeit subtle, hand in the deep rumblings and upheavals of Earth's interior. Our planet and its closest satellite are intricately connected, not only through the light reflected across the void and the rhythmic ocean tides, but also through the very shaking and shifting of the ground beneath our feet. This connection highlights the profound and far-reaching effects of gravitational interactions throughout our solar system. The moon's persistent pull is a constant, unseen force subtly influencing Earth's geology in ways that underscore the deep, interconnected nature of celestial bodies, even in the seeming quiet of space. It's a testament to the powerful, invisible bonds that shape our homeworld. Beneath its bright, icy surface, Ganymede, Jupiter's largest moon, may possess an incredibly complex internal structure layered like a cosmic sandwich. Scientists hypothesize that instead of a single, continuous ocean, Ganymede could harbor multiple oceans stacked in layers. Imagine a sequence of ice, then liquid water, then another layer of high-pressure ice, followed by yet more liquid water, and so on, reaching miles deep into the moon's interior. This extraordinary layered structure is thought to be possible due to the immense pressures that exist deep inside Ganymede. At extreme depths, water molecules can be compressed into exotic phases of ice, which are denser and behave differently than the ordinary ice we know. These high-pressure ice layers could then act as separators, trapping liquid water layers between them. Combined with its molten metallic core, which generates its own powerful magnetic field, Ganymede reveals itself to be far more complex and active than a typical moon. It truly exhibits characteristics akin to a planet in miniature, complete with its own vast internal oceans, a protective magnetic field, and a diverse geological history. If we possessed the capability to slice into Ganymede, we would uncover layer upon layer of water and exotic ice, forming a frozen, intricate architecture unlike anything found on Earth. This complex internal layering makes Ganymede a fascinating subject for study, offering insights into how large, icy moons can evolve into incredibly dynamic and multifaceted worlds, defying simple classifications. Io, Jupiter's innermost Galilean moon, is arguably the most volcanically active world in our entire solar system. Its incessant eruptions produce immense lava flows that can stretch for hundreds of miles across its turbulent surface. These rivers of molten rock often glow a brilliant red-hot, perpetually reshaping the Moon's terrain in a constant, dramatic cycle of destruction and renewal. Some of Io's eruptions are so powerful that they create plumes of material that rise hundreds of miles above the surface, visible even from the distant vantage point of orbiting spacecraft. Unlike Earth's volcanoes, which are typically scattered and concentrated in specific tectonic zones, Io's volcanoes are virtually everywhere, turning the entire Moon into a shifting, seething volcanic landscape. From orbit, Io's surface appears to glow with the fresh, often brightly colored scars of countless recent eruptions. It's an endless, vivid reminder of the raw, immense power of tidal heating, relentlessly generated by Jupiter's colossal gravitational pull. This constant flexing and squeezing of Io's interior keeps its mantle molten and fuels its incredible volcanic activity. Io is a world in perpetual upheaval, a dramatic testament to the extreme geological consequences of being locked in a close, tidally stressed orbit around a gas giant. It's a fiery spectacle, a cosmic furnace continually remaking itself. Europa's icy surface, a vast, fractured sheet, is a dynamic and ever-changing landscape. It is intricately crisscrossed with an astonishing network of ridges, cracks, and reddish-brown streaks. Unlike the heavily cratered, ancient surfaces of most other moons in the solar system, Europa's appearance is remarkably young and active. This youthful look is due to its ice continually shifting, breaking apart, and then refreezing, a process that effectively erases older impact scars and geological features. Beneath this dynamic frozen crust lies the global ocean, and the internal heat generated by Jupiter's powerful tidal forces keeps the ice above in a constant state of motion. These processes lead to significant resurfacing. Some of the prominent cracks and fissures on Europa's surface may even vent material from the subsurface ocean to the exterior. These plumes or upwellings can deposit reddish stains, thought to be mineral salts or organic compounds, which rise from the hidden waters below. Europa's constantly refreshed surface hints at a restless world, where the frozen crust is not merely a static shell but a thin, dynamic skin overlying a vibrant, living ocean. It suggests a world where geological processes are actively at work, potentially interacting with its vast internal water reservoir, making it a prime candidate in the search for extraterrestrial life. Callisto, Jupiter's outermost large moon, is a true relic of the solar system's deep past. Its surface is so incredibly heavily cratered that it resembles a cosmic fossil, a frozen record from the earliest, most violent days of our solar system's formation. Some of its largest and most ancient impact scars are estimated to be nearly 4 billion years old. These ancient craters have been remarkably preserved because, unlike its more active siblings Europa and Io, Callisto lacks significant geological activity that would otherwise erase such features. There is little to no tectonic movement, volcanic resurfacing, or ice tectonics to smooth over its ancient face. In essence, Callisto is like a cosmic time capsule, offering us a direct visual glimpse into what the solar system was like during its tumultuous youth, a period when impacts from asteroids and comets were far more frequent and violent. Looking at Callisto is akin to gazing backward across eons, peering into a profound chapter of cosmic history that Earth itself has long since erased through its own dynamic geological processes. Its cratered expanse is a silent, enduring testament to the immense destructive power and creative potential of the early solar system, preserved for us to study and wonder at. Despite being perpetually shrouded in a thick, hazy atmosphere, Titan's surface, Saturn's largest moon, is far from flat or featureless. It boasts impressive mountain ranges that rise to heights even greater than Earth's Rocky Mountains. What makes these peaks even more extraordinary is their composition. They are not made of silicate rock like mountains on Earth, but rather of solid water ice. At Titan's incredibly frigid temperatures, water ice behaves like rock, becoming as strong and rigid as stone. These towering icy mountain ranges are thought to have been lifted by tectonic forces, similar to those that build mountains on Earth, or perhaps by a process known as cryovolcanism, where icy material erupts from the moon's interior. To imagine standing beneath these colossal icy ranges would be a truly surreal experience. Mountains of frozen water, glistening under a dim, orange sky, towering majestically over expansive lakes and seas of liquid methane and ethane. Titan's mountains demonstrate that even in the cold, distant reaches of the outer solar system, landscapes can be as dramatic, imposing, and geologically diverse as those found on Earth. They are carved from entirely different materials, yet they possess a grandeur and majesty that is no less awe-inspiring. It's a testament to the diverse ways worlds can be shaped across the cosmos. The tiny, icy moon Enceladus is in a constant state of actively spraying water vapor and fine ice crystals into space from distinct fissures located near its south pole. These remarkable geysers are so powerful and continuous that they actively replenish Saturn's E-ring, forming a diffuse halo of material that gracefully encircles the gas giant. Every single particle within that delicate, shimmering ring may have, at one point, been a part of Enceladus's hidden subsurface ocean, blasted into space by the immense tidal forces exerted by Saturn's gravity. This constant connection between a relatively tiny moon and a vast, intricate ring system beautifully illustrates the subtle yet profound interplay of bodies in orbit. Enceladus, despite measuring only about 300 miles across, leaves an indelible mark on one of the most iconic and beautiful features in our entire solar system. Its continuous offerings to the E-ring are a dynamic testament to its internal activity and the powerful gravitational relationship it shares with Saturn. It's a striking example of how even the smallest celestial bodies can have an outsized and lasting influence on the larger structures within a planetary system, constantly shaping and redefining their cosmic environment. Triton, Neptune's largest moon, is cloaked in a surface composed primarily of nitrogen ice. This unique composition gives it a pale, somewhat otherworldly appearance. Unlike water ice, which is rigid at colder temperatures, nitrogen ice is surprisingly soft and mobile at Triton's incredibly frigid temperatures, allowing the moon's landscape to subtly shift and smooth itself over vast periods. When the Voyager 2 spacecraft made its historic flyby, it revealed active geysers on Triton's surface, venting plumes of nitrogen gas and dark particulate matter high into its thin atmosphere. These eruptions leave behind distinct dark streaks that crisscross the icy plains, visible signs of ongoing geological activity. These geysers are compelling evidence that Triton, despite its immense distance from the Sun and the extreme cold, is still an active world, continually reshaping itself even at the very edge of the solar system. Its surface is notably smoother compared to many other heavily cratered moons, a characteristic that further suggests it is constantly being renewed and resurfaced by this unique icy activity. To imagine walking on Triton would be to step across vast fields of frozen nitrogen, a truly alien landscape where the ordinary state of ice behaves in strange and subtle ways, revealing the incredible diversity of materials and processes that shape worlds in the outer solar system. Charon, Pluto's largest moon, is scarred by a canyon system so immense and vast that it utterly dwarfs anything found on Earth. This colossal chasm stretches for over 1,000 miles across Charon's surface and plunges to depths that are nearly 4 times greater than the Grand Canyon. Scientists believe this gigantic feature formed as Charon's icy interior expanded over time, causing its rigid crust to crack open dramatically. The sheer scale of this canyon system makes it one of the most breathtaking and dramatic geological gashes observed anywhere in our solar system. If it were possible to stand at its edge, gazing down into its profound depths, one would witness colossal walls plunging into perpetual shadow, cliffs so immense they would completely swallow Earth's greatest terrestrial landscapes. While Charon may be relatively small when compared to the major planets, its rugged and extreme terrain unequivocally proves that even smaller worlds can bear colossal scars. These features are a testament to the powerful internal processes and forces that can shape and deform celestial bodies, regardless of their overall size. Charon's Grand Canyon is a silent monument to its violent, expanding past, a geological wonder hidden in the distant, cold reaches of our solar system waiting to be fully understood. Miranda, one of Uranus's smaller moons, hosts one of the most astonishing and dramatic geological features ever discovered in our solar system, Verona Rupes. This isn't just a cliff. It's an immense escarpment estimated to be up to an astounding 12 miles high. To put that into perspective, falling from its dizzying edge would take a staggering 10 minutes to reach the bottom, plummeting through the moon's near vacuum. Scientists theorize that Miranda's bizarre, jumbled surface, including these towering cliffs, is the result of a catastrophic past event. It's thought that the moon was once shattered into countless fragments by a massive collision, and then, under its own gravitational influence, these pieces slowly reassembled. This reassembly process would naturally leave behind the patchwork terrain and the colossal, mismatched cliffs we observe today. Verona Rupes stands as a profound monument to that incredibly violent past, its dizzying scale unmatched anywhere else we know in the solar system. On such a small moon, which is only about 293 miles in diameter, the sight of a cliff that is taller than Mount Everest stacked 3 times over is almost unthinkable, a true geological wonder compressed onto a tiny, heavily scarred world. It challenges our understanding of how extreme topography can form on celestial bodies and serves as a powerful reminder of the destructive and reconstructive forces at play in the early solar system. Unlike the well-ordered moon systems of Jupiter and Saturn, which largely formed from the same rotating disks of gas and dust as their parent planets, Neptune appears to have acquired many of its companions from external sources. Many of Neptune's moons follow unusual, highly tilted, or even retrograde orbits, circling the planet in the opposite direction of its spin. These orbital eccentricities are strong indicators of capture events. Triton itself, Neptune's largest moon, is widely believed to have once been a dwarf planet, perhaps originating from the distant Kuiper belt, before Neptune's powerful gravity eventually pulled it into its current, unusual orbit. These capture events would not have been gentle. They would have been incredibly violent and disruptive to Neptune's original system of moons, likely scattering them, breaking them apart, or even completely destroying them. The result is a planetary system that feels somewhat assembled from fragments, a collection of wanderers gathered into Neptune's gravitational embrace from the far reaches of the outer solar system. Observing these moons is like examining cosmic fossils of ancient migrations, silent reminders of how dynamic, chaotic, and unpredictable the solar system's past truly was. They tell a story of gravitational encounters, close calls, and the powerful forces that can fundamentally reshape planetary systems over billions of years, creating the diverse and often strange configurations we see today. Phobos, Mars's larger but doomed moon, is not a perfectly smooth or pristine body. Its surface is noticeably etched with a series of long, shallow grooves and distinct cracks that stretch across its terrain. For decades, scientists debated the precise cause of these enigmatic markings. Were they simply secondary craters formed by ejecta from a massive impact? Or were they somehow related to tidal forces? The leading scientific explanation now points to a much more dramatic and ominous origin. These grooves may be early signs that Phobos is slowly but inexorably breaking apart. Mars's relentless gravitational pull exerts immense tidal forces on its small moon, constantly stretching and squeezing it. Over millions of years, these stresses are believed to be tearing the moon from within, initiating its slow motion destruction. The grooves on Phobos may well be the very first fractures, the visible evidence of this internal stress and its impending fate. If this theory is correct, then Phobos is a world already wearing the visible scars of its eventual demise. It's a stark and poignant image, a small moon, silently bearing the marks of its own destruction, circling its parent planet on a slow, one-way journey. These grooves serve as a powerful and ongoing reminder of the destructive power of tidal forces and the precarious existence of moons that orbit too close to their planetary hosts, a slow motion unraveling etched into its very surface. Deimos, Mars's smaller and more distant moon, is a tiny, irregularly shaped rock, significantly smaller than its companion Phobos. It orbits much farther away from Mars compared to Phobos's close-in, rapid path. What makes Deimos particularly unique is its remarkably high and smooth orbit. From the surface of Mars, Deimos would appear as little more than a faint star, drifting incredibly lazily across the sky. Unlike Phobos, which races overhead, traversing the Martian sky in just a few hours and setting quickly, Deimos rises and sets at such a leisurely pace that it hardly seems to move at all. Its slow, deliberate motion makes it appear almost motionless against the backdrop of space. To stand on Mars and observe Deimos would be to witness a quiet, gentle presence, a stark contrast to the dramatic, swift passage of its larger, doomed sibling. This difference in orbital dynamics makes the Martian sky a stage for two very different lunar experiences. Deimos, with its almost imperceptible motion, embodies a sense of cosmic tranquility, a subtle and enduring companion. Its stillness provides a fascinating counterpoint to the more dynamic and tragic narrative of Phobos, highlighting the incredible diversity even within a single planetary moon system. It's a reminder that even among close companions, fates and appearances can vary wildly. Not every moon in the solar system shines brightly, reflecting the sun's light like a polished pearl. Some are remarkably dark, absorbing almost all the sunlight that falls upon them, reflecting only a tiny percentage of the incoming light. These are often as dark as coal, or even darker. Jupiter's irregular moon Himalaya, for instance, and many of Saturn's small, outer moons fall into this category. Their incredibly dark surfaces strongly suggest that they may be captured asteroids, having originated from the outer, primitive regions of the solar system. These captured bodies are often coated in carbonaceous material, a very dark soot-like substance that absorbs light efficiently. These dark moons often hide in the profound shadows of space, remaining virtually invisible to the naked eye, even if one were standing relatively close by. Their profound darkness speaks volumes about their origins in the cold, primordial outer solar system, a region where sunlight barely penetrates and where icy, rocky bodies retain their ancient, dark compositions. They are among the dimmest wanderers, worlds that seem to whisper rather than gleam, offering a silent testament to the vast diversity of celestial bodies and the varying conditions that shaped them throughout cosmic history. On the complete opposite end of the spectrum, some moons are extraordinarily bright, reflecting nearly all the sunlight that strikes their surfaces. Enceladus, one of Saturn's moons, is a shining example. Covered in a continuous layer of fresh, pristine ice, constantly replenished by its active geysers, it gleams with an almost blinding brilliance, reflecting nearly 100% of the sunlight it receives, making it one of the most reflective objects in the solar system. Its albedo, a measure of reflectivity, is exceptionally high. Seen from space, it truly shines like a pure, white pearl, dazzling against the profound blackness of the void. This extraordinary brightness isn't just aesthetically stunning, it provides valuable scientific information. It tells astronomers that Enceladus's surface is continually being renewed, coated with fresh ice from its internal ocean. Where darker moons reveal their ancient age through impact scars and accumulated cosmic soot, bright moons like Enceladus proclaim their youth and ongoing geological activity. Their brilliant shine is a direct signal of life within, of dynamic processes constantly reshaping and resurfacing their exteriors again and again. It's a vivid demonstration of how a moon's appearance can be a direct window into its internal workings. Around the colossal giant planets, moons don't always orbit in solitary splendor. Instead, many dozens of small, irregular moons can form loose groups or clusters, circling their parent planet together, almost like miniature, chaotic solar systems. Many of these clustered moons share similar, highly tilted or elongated orbits. This orbital consistency strongly suggests that they are not individually formed bodies, but rather fragments of a single, larger body that tragically broke apart long ago, perhaps due to a catastrophic collision or intense tidal forces. Both Jupiter and Saturn host numerous such moon families, each a collection of shattered pieces still bound together by the planet's immense gravity. Studying these clusters of irregular moons allows scientists to piece together the violent histories of these systems. They reveal past collisions that tore apart larger worlds into swarms of smaller ones, creating these unique, fragmented families. Today, these numerous little fragments drift in quiet, collective company, forever bound to the colossal giants they circle. They are cosmic remnants, silent witnesses to ancient cataclysms, yet still participating in the grand orbital dance, a testament to the enduring power of gravity to hold even shattered worlds together. When Galileo Galilei turned his rudimentary telescope towards Jupiter in 1610, he made a discovery that would forever change the course of science. He observed 4 tiny points of light, positioned very close to the giant planet. Night after night, as he meticulously observed them, he noticed that these stars shifted their positions relative to Jupiter. This careful observation led him to an undeniable conclusion: these were not fixed stars, but rather moons orbiting Jupiter itself. This groundbreaking discovery sent shockwaves through the scientific and philosophical communities of the time. It provided irrefutable evidence that not everything in the heavens revolved around Earth, directly challenging the long-held geocentric model of the universe, which placed Earth at the center of all celestial motion. Instead, it lent powerful support to the burgeoning heliocentric idea, which proposed that planets orbited the Sun. These 4 moons, now famously known as the Galilean moons, Europa, Ganymede, and Callisto, became the very first celestial bodies beyond Earth known to humankind to possess their own satellites. They remain, to this day, 4 of the most fascinating and intensely studied bodies in our solar system, each uniquely revealing something new and profound about planetary systems in general. Their discovery was more than just an astronomical observation. It was the critical first step towards a new understanding, fundamentally reshaping humanity's perception of its own place in a vast, complex, and dynamic universe. It was a profound intellectual revolution. In 1610, when Galileo Galilei aimed his handcrafted telescope at the night sky, he peered at Jupiter and noticed 4 distinct points of light hovering near the colossal planet. Through successive nights of careful observation, he saw these points of light shift and move, clearly orbiting around Jupiter. This was a radical revelation. These were moons Europa, Ganymede, and Callisto, and their very existence and motion provided undeniable evidence that not all celestial bodies revolved around Earth. At a time when the vast majority of people, supported by centuries of philosophical and religious doctrine, still believed in a geocentric universe with Earth at its absolute center, Galileo's discovery was nothing short of revolutionary. It provided concrete, observational proof that planets could possess their own satellites, moving independently of Earth's orbit. This marked a monumental turning point in scientific thought, fundamentally shaking ancient assumptions and paving the way for the modern, heliocentric view of our solar system. The sight of those 4 small moons, faithfully circling Jupiter, was far more than just an astronomical discovery. It was empirical abrasive. It wore down and cut through the tough fabric of their spacesuits, scratching visors, and even clogging delicate equipment. Breathing it in was, and remains, a significant health concern, as its fine, sharp particles could easily lodge deep within the lungs. To walk on the moon, therefore, is to step into a field of invisible, relentless, tiny knives. The dust itself is a geological record, a silent archive of billions of years of impacts. It also represents a significant and ongoing challenge for any future human missions that plan to return to the lunar surface. It's a harsh, alien substance, far removed from anything we encounter in our daily lives on Earth. The moon's gravitational pull isn't limited to just raising the tides in our vast oceans. It also exerts a subtle but constant tug on the solid body of Earth itself. This relentless pull causes our planet to bulge slightly in the direction of the moon, making Earth subtly, almost imperceptibly, egg-shaped. The effect is incredibly tiny, utterly invisible without the aid of highly precise scientific instruments. Yet, it serves as a powerful reminder of just how profoundly and pervasively the moon influences our world. Its gravity penetrates through rock, water, and air, gently but persistently deforming our planet. Earth and its moon are locked in a perpetual gravitational embrace, an intricate dance that shapes one another in ways we rarely notice, but which ripple across the entire Earth-Moon system. It is a testament to the immense, far-reaching power of celestial mechanics binding 2 worlds together. A moon that ventures too close to its parent planet faces a truly perilous existence. There's a critical boundary, an invisible line in space known as the Roche limit. If a moon crosses this specific distance, the planet's immense gravity begins to exert an incredibly powerful differential pull. It tugs harder on the side of the moon facing the planet than it does on the side facing away, effectively stretching the moon apart. Should these tidal forces become stronger than the moon's own self, gravity, which holds its material together, the moon can be completely shattered. Astronomers widely believe that Saturn's spectacular, iconic rings may have formed precisely this way, from a moon that wandered too close to the giant planet and was ripped into countless pieces. In the distant future, Mars's tiny moon Phobos is predicted to meet a similar fate, slowly but surely being torn into a chaotic field of rubble. The very idea that a solid, unified world can unravel into innumerable fragments vividly illustrates how fragile even moons can be when subjected to the immense, relentless gravitational grip of their parent planets. It's a dramatic cosmic process of destruction and transformation. Many moons across our solar system are tidally locked, a fascinating state where they always present the exact same face to their parent planet. Our own moon is the quintessential example of this phenomenon. It rotates once on its axis in precisely the same amount of time it takes to complete one orbit around Earth. This perfect synchronization is why we consistently observe only one side of its surface. Tidal locking is not an instantaneous event. It occurs gradually over immense spans of time as a planet's gravity slowly, but surely slows down a moon's rotation until it perfectly matches its orbital period. The result is a profound gravitational rhythm, a stable balance that almost feels like a carefully choreographed dance. While it means one hemisphere of the moon is forever hidden from its planet's view, it also creates a remarkable stability within many planetary systems. Moons locked in this eternal, synchronized, turn beautifully demonstrate how gravity meticulously shapes both time and motion into a harmonious, enduring celestial ballet. Not all orbits in the cosmos are fixed and unchanging forever. Some pairs of moons engage in an incredibly delicate and intricate gravitational exchange, essentially swapping places with each other. Saturn's tiny moons, Janus and Epimetheus, offer the best known example of this rare celestial phenomenon. They circle the ringed giant in nearly identical orbits, incredibly close to one another. However, instead of an inevitable collision, they perform a graceful orbital switch every few years. As the slightly faster inner moon catches up with the outer moon, their mutual gravitational attraction causes them to exchange orbital energy. This transfer nudges the inner moon into a slightly higher, slower orbit, while the outer moon simultaneously drops into a slightly lower, faster orbit. This cosmic switcheroo has been repeating flawlessly for millions of years, a perfect balancing act. It reveals how even tiny moons can cooperate in surprising gravitational ways, finding remarkable stability through continuous motion. Observing them trade places is like witnessing gravity itself writing a complex, beautiful choreography across the heavens, a testament to the intricate dynamics of planetary systems. The moon's immense gravitational pull isn't solely responsible for raising tides in our oceans. It also exerts a subtle but constant tug on Earth's solid crust. The stresses induced by these lunar tides can, in certain circumstances, act as a trigger for earthquakes or even influence volcanic eruptions, particularly in regions where geological activity is already on the brink. Scientists refer to these as tidal stresses. While these stresses don't directly cause major seismic events or eruptions, they can provide the crucial, tiny nudge needed to push already unstable fault lines or pressurized magma chambers past their breaking point at just the right moment. It's truly astonishing to consider that our moon, positioned so far away in space, can play a role in the deep rumblings and geological processes occurring within Earth's interior. Our planet and its faithful satellite are connected not only through the interplay of light and tides, but also through the very shaking and shifting of the ground beneath our feet, a testament to their profound cosmic relationship.